6.5. Entropy change of an ideal gas. We are going to calculate the entropy change of an ideal gas between two states. Recall that real gases like air, hydrogen, oxygen, nitrogen, and helium may be considered as ideal gas at low pressures or high temperatures. An ideal gas obeys ideal gas law or ideal gas equation of state. PV equals RT. P is the absolute pressure, V is the specific volume, R is the gas constant, T is the absolute temperature. The internal energy and enthalpy of an ideal gas depends on temperature only. From the definition of CV and CP, we got du equals CV dt. And dH equals Cp dt for ideal gas. So these are the relations for ideal gas. And we're going to apply the TdS equations for ideal gas. TdS equals du plus PdV. So divide the equation by the absolute temperature. So ds equals du over T plus P over T dV. For ideal gas, du equals Cv dt. And from the ideal gas law, P over T equals R over V. So we got the differential entropy change of an ideal gas is Cv dt over T plus R dV over V. Integrated from the initial state 1 to final state 2 for each of these terms. So what I have is the entropy at the final state with temperature T2 and specific volume V2, or simply put it S2 minus S1 equals integral from T1 to T2 Cv dt over T. R is a constant, so we can take R out of the integral. Integral 1 over V is natural log V. So result of integrations is R natural log V2 over V1. Cv is typically a function of temperature. So we should know the relation between the specific heat Cv and temperature to perform the integration. That is not the only one we need to know to get the entropy change. We also need the specific volume ratio, V2 over V1, between the two states. So remember that the entropy change is not a function of temperature alone. We can also integrate the second TdS equation for ideal gases. Divide the equation by the temperature. ds equals dH over T, absolute temperature, minus V over T dP. dH equals Cp dt over T. From the ideal gas law, V over T equals R over P. So take integral of these terms, S2 minus S1, integral Cp dt over T minus R, natural log P2 over P1. We also need to know the relation between Cp and T to take the integrations. The specific heat, Cv and Cp, are function of temperature. So if the functions are given, you can take the integrations to calculate the entropy change. If CV and CP functions are not given, there are two methods to calculate the integrations. So first method is to use the standard entropy. For ideal gases, the entropy change is not only dependent on the temperature, but also the specific heat and the pressure ratio between the states. So there are no thermodynamic table that give entropy values for ideal gases. Cp is a function of temperature, so we cannot perform the integration without knowing the relation between the specific heat and temperature. So we are introducing new term, the standard entropy. It is denoted by S degree. It is the integral from some reference temperature T prime to temperature T of Cp dt over T. So this is the temperature dependent part of the entropy change. So this term becomes S degree at T2 minus S degree at temperature T1, because this is the integral T1 to T prime Cpt T dt plus T prime to T2 Cpt T dt. And this integration equals negative integral T prime to T1 of Cp dt over T. So this equals S degree at temperature T1. This is S degree temperature T2. So standard entropy also have the unit of entropy, kilojoule per kilogram Kelvin. Note that the standard entropy is a function of temperature only. So since standard entropy is a function of temperature only, we can tabulate the standard entropy. And also note that the standard entropy is defined in terms of constant pressure specific heat, and we don't define the standard entropy in terms of constant volume specific heat. Let's see this example. Evaluate the change in specific entropy in kilojoule per kilogram Kelvin of air modeled as an ideal gas from a state where T1 300 Kelvin and P1 1 bar to a state where T2 1000 Kelvin and P2 3 bar. Although we know the temperature and pressure at the initial and the final states, so we can fix the states, but entropy cannot be found from the table. Entropy at the given condition cannot be found directly from the thermodynamic table. So first we need to determine the standard entropy at the given condition. So entropy change between the two states is S degree at temperature T2 minus S degree temperature at T1 minus gas constant R natural log P2 over P1. So standard entropy at temperature 1000 degree. S degree is 3.52364. The initial temperature 300 Kelvin, standard entropy 2.35531. Gas constant for air. Universal gas constant divided by the molecular weight of air. Natural log pressure 3 bar over 1 bar equals 0.9504 kilojoule per kilogram Kelvin. So note that the standard entropy is only function of temperature, and we can find the standard entropy from the table. The second method is to assume constant specific heat. The specific heat is a function of temperature. We discussed before that the specific heat may be assumed to be constant within a small temperature range. Note that this is an approximation. The first method, using thermodynamics tables, provides more accurate result. If the specific heat is a constant, we can take the specific heat out of the integration. So the equation can be simplified. You can take the average of specific heat between the two temperatures. So integration Cv dt over T becomes this one. Integration Cp dt over T becomes this one, assuming specific heats are constant. So can we use these two equations to determine the entropy change of an ideal gas undergoing an irreversible process? Yes, TDS equation was derived for internally reversible processes, but the equations relate the properties at the end stage only, so they may be used for irreversible processes. Let's see another example. Evaluate the change in specific entropy in kilojoule per kilogram Kelvin of air modeled as an ideal gas from a state where T1 300 Kelvin, P1 1 bar, to a state where T2 400 Kelvin and P2 5 bar. Because of the relatively small temperature range, we assume a constant value of Cp, specific heat at constant pressure, evaluated at 350 Kelvin. Use Cp 1.008 kilojoule per kilogram Kelvin. So we take the second method to determine the entropy change between the two states. So since Cp is constant, S2 minus S1 is Cp natural log T2 over T1 minus R natural log P2 over P1. So Cp is 1.008 kilojoule per kilogram Kelvin, T2 400 Kelvin, T1 300 Kelvin, gas constant, universal gas constant divided by molecular weight of air, natural log, pressure P2 5 bar, P1 1 bar. This is negative 0.1719 kilojoule per kilogram Kelvin. So again, we assumed constant specific heat, Cp. So if the table is available, the best way to get the accurate result is to use the tables. If the thermodynamic tables for entropy is not available, we assume specific heat is constant and simplify the equations.